So now let's do our first example. Let's solve the differential equation y prime equals 3y. Now, I want to tell you that the power series method is terrible for solving this problem. This problem is ridiculously easy. The answer is y equals c e to the 3x, right? This is a separable equation. We could have done this on day one. You probably could have done this back in Calc 1 or 2. Power series are bad for this. But I want to get used to using power series to solve differential equations. So what I want to do is I do want to go through the process of solving this using power series. And so what we're going to do is we're going to start by, and this is how all our power series method problems are going to start for the most part, but this is where we're going to start. Suppose that we don't know what the solution is going to be, but suppose that our solution is going to be some power series y. So I'm going to write y as the sum from n equals 0 to infinity of c sub n x to the n. And what we're going to do is we're going to figure out what's the sequence c sub n that'll satisfy this, that'll give us our function where the function satisfies this differential equation. So what we need to do is we need to compute y prime. And y prime is going to be, we're just going to assume that everything is nice. We're going to work inside the interval of convergence, so we can just differentiate term by term. And when we differentiate, this is, of course, c0. So the original function is c0 plus c1x plus c2x squared, and so on. So that means that when we differentiate, we're going to end up with c1 plus c2x plus 3c3x squared, and so on. So in general, you end up with n c sub n x to the n minus 1, starting at 1. The sum could start at 0 if you want, because the 0th term is just 0, because you have a 0 there. You have an n there, I mean. So when n is 0, that's just 0. And also just notice that all we really did is we differentiated term by term. The derivative of x to the n is n x to the n minus 1. The c sub n just hangs out here because it's constant with respect to x. And then our index increased by 1 because the first term was a constant. So that means that we don't need to include it. Although you can. It's the same sum starting at 0 or 1. So now what we're going to do, so let me get rid of this work down here. This was just to kind of show you why all these things happen, why they all work the way they do. But this is how this is going to work. And in general, you can find the second and higher derivatives in the same process. So what we're going to do now is we're going to take these expressions for power series and plug them back into the differential equation and then just see what happens. So if y prime is this sum, our differential equation is going to become, this is the sum from n equals 1 to infinity of c sub n times n x to the n minus 1. And that's going to be equal to 3 times y. So this is going to be 3 times the sum starting at 0 to infinity, c sub n x to the n. Now, a few comments here. What we're going to have to do is we're going to have to shift this sum. Basically, we have two power series that we're setting equal to each other. We need them to have the same power of x, and we need them to start in the same place. Okay, so they need to have the same starting index. What we're going to do, though, is we need to manipulate them somehow. And so for this right sum, we're just going to move this constant inside the sum, right? If this is a sum of terms, then you can move the constant inside. Everything's fine, even if it's a finite, even if it's an infinite sum. Okay, so everything's fine. On the other hand, over here, we'll need to be a little bit more careful. So let's leave the left side just for now. And then for the right side, let's just move the 3 inside. So we're not really doing a big step there. So this is going to be 3 c sub n x to the n. The sum is still going to start at 0, so we're not changing any of that. Now, the left sum, what we're going to do is I want to make this so that the sum starts at 0. And there's a few different ways to think about this. And in fact, we did this in one of the introductory videos on power series. What you can do is you can change this so that you could call, for example, k is n minus 1, so that n is k plus 1. So this tells you n is k plus 1. And then this is going to be the sum going from well, if n is 1, k is 0, and all your n's get replaced by k plus 1s. Okay, so all your n's get replaced by k plus 1s. This still goes to infinity. And we're going to kind of mentally do this each time, except I'm not going to use a different variable. I'm just going to use the same variable. So I think a better way to think about this is that if I start this sum at 0, n equals 0, what I have to do then is we have to change all of our n's to n plus 1s. And the reason why they change to n plus 1s is that think about what's the smallest term that you get in this original power series. When n is 1, you're going to have a c1 times 1 x to the 0. And so what you want here is you want to put the subscript so that the first term you're going to get is c1 times 1. So this is going to be c sub n plus 1 times n plus 1 x to the n. Okay, and so you can do this trick. Again, if you want to think about the intermediate step of replacing n with k minus 1, or equivalently replacing k with n plus 1, then you can do that. I think it's better just to ignore the other variable and just change this from the sum starting at 1 to the sum starting at 0. And the cost is that you have to add. So since we're changing our index down by 1, we have to add 1 to our values of n. So our n becomes n plus 1. So the n's all become n plus 1s. Okay, so of course this is n plus 1 minus 1. So I'm just going to write x to the n. But once we've done that, and this is going to be a pretty common thing that we'll have to do in the power series problems. Once we've done that, notice that we now have our power series exactly like we want them. We both have, they both have x to the n terms. They both start at 0. And so what this tells you is that c sub n plus 1 times n plus 1 is going to be equal to 3 times c sub n for all values n greater than or equal to 0. Okay, so this is going to be our sequence here. Okay, so c sub n plus 1 is going to be n. Do I have a slight mistake here? No, everything's fine. So c sub n plus 1 times n plus 1 is going to be 3 times c sub n for all n. And so what we can do is, I'm just going to call this original value c naught. I'm just going to call this capital A. And then we're going to write all the other terms in A. So we're going to write all the other terms using A. So C1, so here I'm going to think about, let me just take one step back here. I'm going slightly too quickly. C sub n plus 1 is defined as 3c sub n over n plus 1. This is how the sequence is going to be defined for all n greater than or equal to 2, 0. Now I don't give you the initial value, and we'll see how that works. So let's just say that the initial value is a. So if the initial value is a, then let's think about what's c1. Well, c1 is what we're going to get when we plug in n equals 0. So that's going to be 3 times the previous term over 1. So in our case, that's going to be 3a. C2 is going to be 3 times the previous term divided by 2. So this is going to be 3 times the previous term divided by 2. I am not going to simplify since we're trying to find a pattern here. I am not going to simplify. And then C3 is going to be 3 times the previous term divided by 3. So this is 3 times 3a over 3 times 2. And let's do just 2 more. Hopefully the pattern will emerge here. By the way, this is 3 cubed times a over 3 times 2. And then C4 is going to be 3 times the previous value. So that's going to be 3 to the 4 times a divided by 4. So that's the previous value here is this quantity, except it's 3 cubed. And then we're going to divide. So we multiply by 3 and then we divide by 4. So there we go. And then just one more term, C5. It's going to turn out to be 3 to the 5th times a over 5 times 4 times 3 times 2. And of course, this is 3 to the 5th times a over 5 factorial. And so if we try and come up with a pattern for this, it turns out that our sequence C sub n is going to be 3 to the n times a over n factorial. That's what our pattern is. And you can check that this holds for all values n greater than or equal to 0. Now, once we have that, this tells us that our solution to this differential equation y prime equals 3y is this power series y, which is c sub n, which we said is 3 to the n times a over n factorial, x to the n. And this is going to be the sum from n equals 0 to infinity. Now, a is a constant that we can just bring outside the sum like we did before. So this is a times, let's actually just write it below it. This is a times 3 to the n x to the n over n factorial. This, by the way, is where we needed, there were power series that I told you that you needed to know. This is where they come into play. So this is where they're relevant. This is now a times this, the sum of 3x to the n over n factorial. And that looks a lot like, this is an n in the denominator, by the way, not a u. I've never been able to write n's properly. Okay, and so this is, this should remind you of the exponential function. This is a times e to the 3x, because we know that e to the t is the sum of t to the n over n factorial, where n goes from 0 to infinity. So our t is 3x, so this is really a e to the 3x. And this confirms what we already knew, right? We knew this like 20 minutes ago. The solution to this differential equation was a constant times e to the 3x. Notice that the constant that we get is our C0 term, right? So our C0 term, which we called A, is the constant that we get. So this is the first value that we get in the sequence. So it turns out that that's going to determine what this sequence is going to be. Okay, so that's going to be our solution there. Okay, so again, not a good method at all for solving this problem. There's a much easier method. In fact, there's lots of other easier methods, but hopefully this illustrates the ideas that we're going to start to play around with, and in some of these equations it'll be tougher to solve.